Thank you for the opportunity to give this talk. This is going to be about joint work in progress with James Penner, whose goal is to compare two conjecturally equivalent formalisms for unitary chiral conformal field, namely unitary vertex operator algebras and conformal nets. So a unitary VOA consists of a vector space, two distinguished vectors called the vacuum and the conformal vector, the state field correspondence, and then the part that corresponds to the fact that this is a unitary VOA, namely an inner product, a Hermitian inner product on V, and an involution, an antilinear involution. And those are subject to the following set of axioms. We have the axiom that tells you how the vacuum acts on any given vector and how any given vector acts on the vacuum. We have the celebrated locality axiom. Then we have the axioms that make this into a vertex operator algebra, namely that the modes of the field associated to the conformal vector satisfy the Virasoro algebra relations, that L0, the zero mode, is the grading, and that L-1 is the translation of. Finally, we have the axioms that relate to the fact that this is a unitary VOA, namely that this involution theta is an antilinear VOA automorphism, i.e. Fixes the vacuum and the conformal vector and is compatible with a state field correspondence. And finally, we have an axiom that might seem a bit daunting, that relates the involution theta with the inner product. And the way I like to think about this, so let's see. So here we have an insertion of the element theta u. So let's write theta u. I think of it as being inserted at the point z bar of the complex plane. So this is how I like to represent this here. And let's draw the corresponding thing for this. So instead of thinking of it as being this whole thing, I'm just going to think of it as the element u, just itself, inserted at the point z inverse, except whereas here we had the standard coordinate, zeta goes to zeta plus z bar, here we have a modified coordinate, and that's what this whole thing is about. And the coordinate is zeta goes to zeta plus z inverse. And so I think this really helps in parsing what this thing is really about. And one can even make it more clear by, instead of using theta u, let's just use u itself. And instead of using this coordinate here, let's use theta goes to zeta plus z bar. And when you do it that way, you see that these two local coordinates are related by inversion along the unit circle. The map z goes to z bar inverse. And so, okay, this is what it means in algebra, but this is a picture that I have in mind when I think about that form. Now let me tell you about conformal nets. So a conformal net consists of Hilbert space together with a distinguished vector, omega, again, called the vacuum. We have a projective unitary representation of positive energy of the group of orientation preserving diffeomorphisms of S1 on H And that is denoted by an element phi goes to u sub phi. And u sub phi is, of course, not well-defined. It's only well-defined up to phase because this is a projective representation. And then the most important piece of data says that for every interval of the circle, then we assign a von Neumann algebra a subalgebra of the algebra of bounded operators on our given Hilbert space. And being a von Neumann algebra means that it's closed under a certain topology on B of H known as the weak operator topology. And these data are subject, as usual, to a set of axioms. If an interval I is smaller than some interval j, then we want the corresponding algebra A of I to be smaller than A of j. If two intervals are disjoint, then we want the corresponding algebras of operators on H to commute, namely any element of A of I should commute with any element of A of j. This is the locality axiom for conformal nets. And then we have these two axioms that have to do with covariance with respect to the action of diffeomorphisms, namely that if you conjugate an algebra by the unitary corresponding to diffeomorphism, you get the algebra of the translated interval phi of A. And at last, we have that omega should be cyclic, meaning that if you hit it with elements of A of I's for all the intervals, then the set of vectors that you get in H is dense. That's what it means to be cyclic. And it should also be fixed under the Möbius subgroup of diff square. These axioms have some interesting consequences, of which I'm going to list a couple, the ones that are going to be relevant for us right now. So one very interesting one is that A of I makes sense not just for subintervals of S1, but for any abstract interval, i.e. just an abstract one-dimensional manifold that's isomorphic to the interval 0, 1. And produces an abstract von Neumann algebra, i.e. a von Neumann algebra that's not embedded inside B of H, inside the algebra of bounded operators on a Hilbert space. So this is one consequence that we have, and then another one that I want to list is the so-called Ray-Schlieder theorem, which says that the vacuum vector is in fact cyclic for every one of these local algebras individually. We had asked that it is cyclic for the action of all of them, but it is actually cyclic for each one of them individually. And maybe a comment about this first consequence on the side of VOAs. This reminds me, this is quite an analog of the fact that if I have some point z inside some abstract Riemann surface sigma, then there is an associated space which is isomorphic to the vertex algebra, but not canonically so, and that corresponds to this point in this Riemann surface. And so this is a bit similar to that. We have an algebra which is isomorphic, but not canonically so, to one of these. Now, a couple of words about the expected relationship between these two things. So I expect these two formalisms to be equivalent. but of course this is presently an open problem. There is substantial work that has been done in constructing conformal nets from VOAs due to Karpi, Kawashigashi, Longo-Weiler. And so what they do is they provide sufficient conditions to be able to construct a conformal net from a unitary VOA. And what I'm going to tell you about today is how to go the other way, how to construct a unitary VOA from any conformal net. And maybe the first things to compare is the vertex algebra V and the Hilbert space H. So H is, of course, just going to be the completion of V with respect to the inner product that we have here. And going the other way, we can recover V from H as being the algebraic direct sum of the eigenspaces of the rotation that is contained inside this diff S1 action. Finally, I want to mention one important consequence of the vertex algebra axioms, namely that this expression, this product of fields, which a priori is only defined when the absolute values of the points at ends are ordered in this particular way, in fact, is well defined and holomorphic everywhere, provided the zi's are different or distinct. Or maybe said in a better way, there is an analytic continuation to a v-bar valued holomorphic function. And the way I like to think about it is in terms of the complex plane drawn with a bunch of points and then the fields inserted at these points. And this v-bar valued holomorphic function really contains essentially all the data of a vertex algebra. And so if starting from a conformal net, I'm able to build these collections of holomorphic functions, then it's only a matter of checking some axioms, but then we have essentially constructed a vertex. I would like to ask a question, which is, what is the analog of these field insertions for conformal nets? So if I take disjoint intervals, if I take elements, in the corresponding von Neumann algebras, then by the locality axiom for conformal nets, the following expression, which is an element of the Hilbert space, is independent of the order. And I like to draw this in the following way. So here are these intervals, which are inside the unit circle, which is inside the complex plane, are the analogs of these points. And the algebra elements are the analogs of these VOA elements. And this is all an element of the Hilbert space, which sits inside, of course, of the algebraic product of its weight spaces. And so we have that this lines up well with this setup where things are in v-bar. Now, I can modify this by interspersing exponentials of L naught. And the way I like to draw it is as follows. So here we have concentric circles of radii strictly decreasing, it is no longer important that the intervals are disjoint because they're put on disjoint circles. This expression here, because of that condition, these numbers are smaller than 1, and so these are bounded operators, and that is then an operator from H to H, a bounded operator. And therefore, this thing here is in H. That one there, however, is not bounded, but it maps H to V bar. Well, it acts on V bar, and H includes in V bar, and so the whole thing ends up being an element of the algebraic completion. More generally, given disjoint intervals, not necessarily arranged along these concentric circles. So just some random embedded intervals into the complex plane. So here's one of them, and here's another one. Let's see, here's one. There. And given elements, in the abstract von Neumann algebras associated to these intervals, what we'd like is to make sense of something that I'm going to draw in this way, analogous to this. So you put this one here, and you put this one there. And so I like to call, so these are called field insertions. And I like to call these worm insertions. So let me define for you what these things are. So the first thing that you do is you pick a sequence of disks in the complex plane such that these intervals lie on the boundaries of these disks. So ith interval is on the boundary of the ith disk. And let's also pick a parameterization, a Riemann map from the standard disk to these disks. So let's draw them so that we have an idea what's happening. So here I would have the first one. Let's draw it fairly big so that it has a chance of containing all the other ones. And then the next one would be like that. Then one that goes around here, and then finally one. So these are the boundaries of these disks, is what I've drawn here. And then what one wants to do is, similarly to this situation where, so this guy here, that operator is the operator corresponding to this annulus here. So now we're going to have operators corresponding to these wiggly annuli. So let's call these annuli, okay, let's pick also a round disk that's sort of bigger than all the other ones. That one is actually round and has a radius, which I'm going to call r. And so this defines a collection of annuli, which are the things in between these different circles that I drew. So let's call them A1, A2, A3, up to N. And then the formula for these worm insertions is, so first we have an operator R to the L naught, similarly to this one. And then we have the first annulus acting then I want to act by this element of that abstract von Neumann algebra, but of course I need to put it back so that it becomes an element of a concrete von Neumann algebra that acts on H. And so I put it back using this phi here. So this is standard disk, and then pulling it back brings this algebra back into the form of a concrete algebra that acts on H. And once again, this whole thing lives in the Hilbert space, and then that brings it into V bar. So now I need to, of course, tell you a little bit more about annuli and what are these operators that correspond to these annuli. So one major insight due to Siegel and Neretin is that the Virasoro algebra integrates to something which is not quite a V group, but a semigroup, the semigroup of annuli. So an annulus, an element of the semigroup of annuli, is just, well, you draw two smooth closed curves in the complex plane, one inside the other, and it is the space that's contained in between the two of them. And these annuli come with chosen parameterizations of the inside boundary and the outside boundary by S1. So chosen diffeomorphism from S1 to those boundaries. And for our work, we'll need a refined version of these annuli where it is allowed for these two boundaries to touch. So here I've drawn it so that over some part, they actually completely touched, and that's allowed. And so in order to make sense of these things, because of course one should think of them not as being with their chosen embedding in the complex plane, but as abstract spaces, one should think of them as ring spaces where the ring of functions on this thing is functions that are continuous, holomorphic on the interior, and smooth on the bound. The semigroup law is given by push out of ring spaces. There's an interesting semigroup which at the Lie algebra level corresponds to the span of the Virasoro generators ln for n greater or equal to -1. And then there is a result due to myself and James Teller that says that any positive energy representation of the Virasoro algebra on some Hilbert space H integrates to a holomorphic representation of, well, not quite this, but the central extension of the semigroup of annuli by bounded operators on this Hilbert space. And of course, slightly less refined versions of this result have appeared earlier by Siegel and Neretin. The novelty here is allowing for these parts where the two boundaries touch each other. The relevance of this sub-semigroup is that by construction, these operators here are in fact in this sub-semigroup. And at the Lie algebra level, because the part of the Virasoro algebra that corresponds to this is one over which the Virasoro cocycle vanishes, then the central extension splits. And so what this means is that these act by honest operators on the Hilbert space and not just well-defined up to phase, and therefore these are actually well-defined. So let me assume for a moment that I have established the equivalence between conformal nets and unitary vertex operator algebras. And let me consider, on the one hand, those elements of V bar that can be expressed as field insertions, i.e. in that way. And on the other hand, elements of V bar that can be expressed as worm insertions, as we have seen. Now here's a lemma that we can prove in that level of generality. Namely, that if I take the linear span of elements that can be expressed as field insertions, this is always a subset of the linear span of elements that can be expressed as worm insertions. For the proof, let me first do the case of a single field. Which, without loss of generality, I'm going to assume to be at the origin of the complex plane. So fix our field, same degree n, and let me also fix an interval, a small interval. So say this is our unit circle, then I'm going to take it to be some epsilon neighborhood of the point 1 in our unit circle. Then let us consider the following. By the Schnitter theorem, we know that the map from A of I to H, sending an element to that element acting on omega, we know that that one has dense image. It therefore also has dense image when viewed as a map into V bar, because H itself is dense in V bar. And then we can consider the projection onto the nth modes of V bar, onto the space Vn. And we can even write the formula for that projection as follows. And this being finite dimensional, and this being a composite of maps with dense images, we learn that this has in fact full image, because there's no such thing as a subspace of a finite dimensional vector space which is dense. It has to be the whole thing. So we learn that this map here is composite. In fact, it's surjective. I.e., what we learn is that there exists an element A in the von Neumann algebra associated to the interval I, such that our chosen V can be expressed as an integral of this averaging operator acting on A omega. Now, let me pick a partition of unit. Where so I'm going to take psi1 to have support up there. So this is the support of psi1, and psi2 So this is an epsilon neighborhood of the upper semicircle and an epsilon neighborhood of the lower semicircle. And therefore, I can split this integral as a sum of two terms, which I have written in this particular way, so that this, which I'll call a prime, and this one, which I'll call a double prime, are elements of the von Neumann algebra associated to, so this one is going to live inside the von Neumann algebra associated to the some 2 epsilon neighborhood of the upper semicircle, and that one in some 2 epsilon neighborhood of the lower semicircle. And therefore, we have written our field as a sum of 2 words, which we may draw as follows. For the general case, we now have n fields. We write each one of these fields as a sum of 2 worms, and we adjust the size of the circle that we use so that it's not too big, so that it doesn't bump into the circles for the other fields. And so what we end up with is a sum of 2 to the n terms, where each term looks as follows. So here we have the points that carried our fields up there, the zi's. Then we have the little circles that we have chosen around each one of them. And then for each such circle, we have a choice of, do we take the upper half of the lower or the lower half? So say here we take the upper half, and here we take the lower half, and here maybe again the upper half, and here maybe again the upper half. And so we have, so V1 we write as a sum of A1 prime and A1 double prime. So here we have the one with a prime, so that's A1 prime. And here A2 double prime. So the 2 to the n terms correspond to choosing between prime or double prime for each one of these field insertions. So this proves our lemma, of course, under the assumption that we have a fully coherent formalism for unitary chiral CFT involving both VOA and a conformal net points of views. But really, what this argument is good for is that suppose we start just with a conformal net, then we can use the right-hand side of this as a definition of the left-hand side. And so this allows us, starting just from a conformal net, to construct for every V1, Vn into V, the desired V-bar valued holomorphic functions that essentially contain the data of a vertex algebra. And so this is, in a nutshell, the idea of how you construct from a conformal net the vertex algebra. Let's go back to this picture with the worm insertions, which, by the way, one of the things that James Henner and I have proven is that this formula here is, in fact, independent of the various choices made, of the various wiggly circles that are drawn in this picture. So if I have worms in C, then we have seen that what we get is an element of V bar. But say that the worms are all contained inside the unit disk. Then what you have is that you may then take this number r, this radius of this outer circle, to be equal to 1, in which case this thing goes away, and note that this expression from here until there is in fact an element of H. And so what we learn is that if we take worms in the unit disk, then we get something which is not just in V bar, but is in H. And another thing we can do is to consider just this expression here. Which is a bound operator from H to H. And if I call A the annulus, which is the product A1, A2 up to AN, then the pictures that I have worms in the annulus, and then what we get associated to that is a bounded linear map from H to H. Now, if I use this trick of writing every field insertion in a unitary CFT as a sum of two worms, first of all, we recover what we already knew, namely that if I put a bunch of field insertions at various points in the complex plane, I get an element of V bar. If the points are inside the unit disk, then we learn that the resulting element is actually in H. And then we also learn this thing about if I have an annulus with a bunch of point insertions, like where I insert fields in that annulus, then we expect a bounded linear map from H to H. So this is the expectation inside a unitary chiral CFT, and this is indeed what we get when we start from a conformal net, but it makes sense to disambiguate from what it is that we expect and what it is that we get, depending on if we start with a conformal net or a unitary VOA. So this is what we get from a conformal net. What we get from a unitary VOA, well, fields in C, that's an element of V bar, yes, of course. If the fields are inserted in the unit disk, then there's a great little argument which I learned from James Tenner that shows that indeed you get something in H, and here's how it goes. An expression like that a priori lives in V bar, but if the absolute values are smaller than 1, that's the important condition, then the series that computes the square norm of that element can be evaluated in this alternative way, and because the absolute values of these points where things are inserted are in decreasing order, the series converges absolutely, ensuring that this square norm is finite, and thus that this element of V bar is in fact an element of H. And then there's a little trick to take care of the case when the inequalities are weak as opposed to strict. So this leaves the case of understanding what happens with fields inserted in an annulus. And this is the case where we don't know how to prove that starting from a unitary VOA, such a picture induces a bounded linear map from H to H. If we knew how to prove it, then we would be able to show the equivalence between conformal nets and unitary VOAs. So the only thing that we get is a linear map which is defined on the dense subspace spanned by such expressions. More precisely, if the analyst A sits inside the subset group of univalent maps, then this is the domain of definition of this operator that one gets. If A is a general analyst, then we need to enlarge slightly this domain by allowing here an analyst to act, and then so this is a slightly bigger, still dense domain of H on which this operator is now defined. This A here is not the same as that one. Given the crucial importance of these operators associated to analyze, let me tell you how one defines them. So we start from a unitary VOA. And so let me assume for simplicity that my analyst is in the semi-group of univalent maps, i.e. can be written as the unit disk minus the image of the unit disk under some holomorphic map f from D to D. And of course, we have now to choose a bunch of points. In the interior of A, which should be, of course, distinct. And elements in the VOA. So given that data, we can define our operator to send a typical element of D, which I write like this, B1 of W1 up to Bm of Wm. And before I write the formula, let me draw the picture for you. So the formula is B1W1, BMWM goes to, and then we put first the AI of ZI's. And then we put the P's not at the points W's, but at their images under F. Moreover, the BI need to be modified by taking into account the change of coordinates induced by the map F. So really here I should have written BI tilde where BI tilde is the image under BI for this particular change of coordinate in the formal neighborhood of the point ZI. So if a VOA comes from a conformal net, then these operators here are bounded. Conversely, if a unitary VOA is such that these operators are bounded for every analyst and every insertions, then following defines a conformal net. So I'm going to take the von Neumann alpha generated by all these operators as the analyst A. So A, remember, comes with boundary parameterizations of the incoming and of the outgoing boundary. So if A has a property that it is supported in I, which means that the two parameterizations agree on the complement of I. So in particular, the analyst is thin on the complement of I. So in this picture, this would be I. This would be parameterized by I, and that part here would be parameterized by the complement of I and the two parameterizations, the incoming and the outgoing parameterizations, would need to agree pointwise on that thin part. So if that's the case, and of course AI are in V and ZI are in the interior of A. So we look at all these operators, and we look at the polynomial algebra generated by these. That's what I call by Vn. Well, we have a polynomial algebra for every interval. These define a conformal net. And a theorem of myself and James Taylor says that, first of all, every conformal net has an associated unitary VOA, and then characterizes those VOAs in the image of that map as exactly being those where these operators, which are defined from D to D, in fact extend by continuity to bounded linear maps from H to H. Moreover, you don't need to check all such things. It's enough to restrict to A being univalent. And we may further restrict to the map F from D to D being a map that sends the origin to itself. And we may further restrict to a single field, so n equals 1. So, in fact, it is enough to check that the following operator is bounded. So it's an operator from V to H, and it sends an element B of V. So So you take the map F that corresponds to the annulus, and you take a point in the interior of that annulus, which I have written in this particular form. And so F induces a local change of coordinate at 0, and that's what I mean by F acting on B. So F and that's the B tildes that I had up here. And so this map, a priori, which is a map defined from V to H, if it's bounded, i.e. if it extends by continuity to a map from H to H, then the unitary VOA comes from a conformal net. And conjecturally, all unitary VOAs satisfy that condition, in which case we would have a complete equivalence between, on the one hand, unitary VOAs, and on the other hand, conformal nets.